Hi there, Year 8. So we've got yet another format for our lesson today. I'm playing around with this a bit, trying to see what works, what doesn't. If you can email me and just let me know which one works best for you, then I'll know how best to plan the lessons going ahead. Because obviously some of you like worksheets, some of you like doing it on the computer. Do we do a mix and match? Do we do it like this? Yeah, we're just figuring it out as we go, like pretty much everyone else at the moment. So yeah, just playing around with formats. So today what I would like to talk to you about is something called Hooke's Law. Now this isn't about a captain on a ship who is cursing a flying boy who never grows old. No, nothing to do with a TikTok croc. No, it's a law that it came up with in 1660. Robert Hooke came up with this law, and so far in physics we haven't found a way of breaking it. Now, as I said to one of my classes, if you want to get into breaking laws and have people celebrate you for it, get into physics, get into science. We love it when people break laws and we get all excited about it, and then you win a Nobel Prize. It's brilliant. I've not managed to do that yet, but I'm keeping on trying. So the law that I would like us to see if we can break today is Hooke's Law. And Hooke's Law states, I'm going to read this one because it is a bit wordy. The extension of an elastic object is directly proportional to the force applied. It's a bit wordy, isn't it? What does it mean? Well, Hooke's Law, the law that Robert Hooke came up with. Yeah? Pretty straightforward. The extension of an elastic object. Okay, so an elastic object is something like an elastic band or a spring, and the extension is how far it extends. Bing! So here we go. I've magicked up an elastic object. Okay, a simple hairband. Hopefully you've all got one of these lying around your house because we're going to need it for the practical experiment tomorrow. Okay, at the end of the video I'll give you a list of things that you will need. Actually no, at the end of the lesson I'll put them on the computer so you don't have to write them down. I'll write them down for you. Okay, so we've got a hairband. It's an elastic object, just like an elastic band, just like a spring, just like anything like that. What do I mean by the extension? Well, as you can see, this hairband has a size, yeah? But I can also pull it, I can extend it. If I apply a force, I can make it bigger. So the extension is how much bigger it gets. I'm going to show you how to measure it. I've got a ruler here. Okay, so if I put the start of my hairband at 0 and move it over, we can see that my hairband is about, sorry, I'll move my fingers. My hairband is about 7 centimetres long normally. But if I keep this at 0 and I apply a force to it, I can extend it. It's now 12 centimetres long. And it goes back to its original shape. It goes back to its original 7 centimetres. Okay? So I can extend it and it will go back into shape. That's what Hooke's Law says. I can change an elastic object and it will go back to its original state. But the extension is proportional to the force. The thing is, I don't know how much force I'm applying to make it change. So we'll have to apply a set force to it tomorrow. Aren't we excited? Aren't we excited? We're going to do a practical and apply set forces. Ooh! Just me then. Okay. So what I would like you to do is to write down Hooke's Law, and you can write it in symbols as well as the words, which is capital F for force equals lowercase k for spring constants, and X, which is for the extension. Oh yeah, the extension, by the way, when I moved it from 7 centimetres to 12 centimetres, my extension was not 12 centimetres. My extension was the difference between 7 and 12. I only extended it by 5 centimetres, okay? So the 7 to 12 was the extension. this part was already there. It wasn't extended. So the extension was only 5 centimetres. We're going to see more of that tomorrow. Okay, so we're going to calculate our extension. Woohoo. Right, so here we go. Hooke's law, the extension of an elastic object is directly proportional, which is kind of the same as or related to the force applied. F equals kx. Can you pause the video and write it down? Thank you. Okay, so here we go. Example 1. I have a spring, and this is going to be on your worksheet. I have a spring which is 5 centimetres long. I extend it to 6 centimetres by using a force of 30 newtons. Okay, what is the spring constant? So spring constant K, and I'm going to put the units in here as well because I haven't given you the units yet. Obviously we know that we do distance in metres and force in newtons. So our spring constant K, what is it? Well, we've got F equals Kx, so our triangle would be like this. And I want to find out K. So Pikachu's going to come in and cover up K. And I find out that we've got force divided by the extension. So K equals our force of 30 newtons divided by, I've got to turn those centimetres into metres, haven't I? So 1 centimetre is 0.01 metres. 6 centimetres minus 5 is 1 centimetre. So I've got 0.01 metres because that's the difference between 6 and 5. Okay, so our extension is the difference, just the bit it's extended, which should give us, now you can do it on a calculator if you want, or you can do it in your head. It should give us 3000, 3000, and then the unit for the spring extension is newtons per metre. Okay, newtons per metre. Let's do another example because we don't want to leave it on its own, do we? Let's give it a friend. Okay, so this time I've got another spring, and this spring has extended from 6 metres to 12 metres. Okay, and the spring constant, so let's figure out the extension first. Okay, so X would be equal to 12 minus 6 equals 6 metres. Okay, and we know that our spring constant is 1000 newtons per metre. Okay, so what force is needed to extend this spring by 6 metres? The force is equal to K times X. Thank you, Pikachu, for helping us there. So the force is 1000 times 6, which is 6000 newtons. So to stretch that spring, it must be a pretty big string. So spring, not string, must be a pretty big spring if we're talking about 12 meters, and it needed 6000 newtons for that. Okay, The other one, I'm not going to do this as an example because you've got quite a few questions to do, so I know you're going to want to stop the video soon and get on with your work. But the other example is how to calculate the extension. Up comes Pikachu, hides the X, so we know that it's force divided by spring constant. Okay, if you do have any questions, please let me know. You can email me, you can email me pretty much. Have a go at the questions. At the bottom of the sheet, there will be a list of things you will need for the practical tomorrow. If you can't get hold of all of them, or if you choose not to have fun with me doing a practical, that's fine. You can use my results and graph my results. But today we're just focusing on doing all the sums. Take care and see you tomorrow. Bye.